Welcome to AP Podcast 11.7. This is Electrolytes in Solution. And really what this is kind of a continuation of our last section on colligative properties, except now we want to make sure that we focus on the fact that when electrolytes break up into water, they break up into more than one component. And as you know, the colligative properties depend upon how many. So that's just a super important topic. And so we've got to deal with a little different formula. Not a huge deal, but we just want to make sure because of this idea right here. It has to do with the number of molecules. So you could probably imagine that if sugar will raise the boiling point a little bit, I think in the last problem we saw it go up by like 0.043 degrees Celsius, right? Ionic compounds should have a bigger effect. Maybe adding salt will bump it up like 0.1 degrees Celsius. We can only find that out if we calculate it out, but we just have to be sure that we're very aware of what's going on when ions break up into water. I've used sodium and chloride over and over so far in this chapter, but don't forget something like this. Let's say we have aluminum nitrate. This isn't two particles. Remember, for every 1 mole of aluminum nitrate, I'm going to get 4 moles of ions, and so we've got to be very, very aware of that. So it turns out that the formulas we've been using are still going to be the formulas we use, except we've got to add another factor. It's called the Van Hoff factor, and it's got this little symbol I. And look at this. This is right out of your book, and boy, I'll tell you, it really seems confusing to me. The moles of particle in a solution versus the moles of solute dissolved. Well, let me look at this. Let's say I've got NaCl, right? Okay. Now, if I have 1 mole of NaCl, how many particles of Na and Cl would I have dissolved in solution? I would have 2, right? So the Van Hoff factor is 2. So basically, even though it seems wordy and it seems kind of technical, all I is how many ions you get when your electrolyte breaks up into water. So that's really all it is. It's not too bad. Now, here's something that's here's something that might not be very obvious, and I've seen this question on an AP test. I've even seen it on my AP test. And so look at this statement right here. The actual value is less. Okay? Now, this is the reason why. If I was expecting sodium and chloride to float around, I would expect to get 2 of those for every 1 mole, right? Well, what happens is when scientists determine what the Van Hoff factor really is, it's usually a number less. And that's, you could probably imagine why. Imagine a big beaker full of pluses and minuses. You know, they're just floating around every so often, right? Now, every once in a while, a plus will come close to a minus, right? In other words, a cation will come close to an anion. And when that happens, they instantaneously, I like to think of it kind of like along the London dispersion forces, but instantaneously, they're going to pair up. Now, if 2 things pair up, then you have 1 thing, right? And so colligative properties is dependent upon how many. So because we get a little what's called ion pairing, the value is a little less, all right? So sometimes you'll actually be asked to find out what I really is, and it's not too bad. But here's our formula. Look at this. Change in temperature equals that factor times the constant times the molality. So that's really the only thing we have to worry about when we're dealing with electrolytes, because colligative properties is completely dependent upon how many particles. So let's look at a couple problems, and then we'll be done with our chapter. Look at this. We've got all these. We've got these solutions. We've got some pure water. I've got water. I've got a solution of, well, that's sucrose, a solution of table salt, and a solution of calcium chloride. Choose one with the. I'll tell you what, pause the video, see what you get, see if your answers match my answers. All right, is that what you got? Now, I gotta be honest with you. I must have got this problem from a book, and unless I'm messing up, this seems like a silly question now that I've done it. I don't know what I was thinking. But let me just go over it quickly so we're all on the same page. Highest freezing point, okay? Well, imagine if you put anything in here. Think about this. We get one particle per every sucrose. We get one particle, well, actually, we get 2 particles for every table salt, and we get 3 particles for every calcium chloride. Remember, if we add a particle, it's going to lower the freezing point, right? So that means pure water is going to give us our highest freezing point. Our lowest freezing point is going to be the thing with the most particles, and that's calcium chloride. Highest boiling point, again, calcium chloride, because that's the most particles. I get 3 for every 1 mole, all right? And then lowest boiling point is pure water. I don't know exactly what the point of that question was, and I apologize for that. But hey, hopefully you got what I got. Hopefully you weren't going, wow, what's he mean by this? The idea is that here we have 1 particle, here we have 2 particles, and here we have 3 particles. All right? Let's get to a problem. All right, here's a problem. Calculate the freezing point and the boiling point of an aqueous solution of 0.05 molal magnesium chloride. Assume complete dissociation. All right, now, we're missing something. We're missing the right equation. I need to have a little I right here, right? So let's work this out. Let's do the boiling point first. So the I factor, what is the I factor? Well, hopefully you're going, well, it's 3. Great. So 3, and this is the boiling point, times 0.51 times the molality, which is 0.05, equals 0.0765, okay, degrees Celsius. Now that's the change, right? So add that to 100 degrees Celsius, and there you get your answer. All right. Same thing with the second one. What's the only difference? Well, I'm going to put this number right there, and when I get that, delta T for the freezing point, I'm going to get a value of 0.279 minus 0 degrees Celsius, right? Which equals a negative 0.279 degrees Celsius. So there you have it. So it's super important that you focus on, am I adding an electrolyte? Am I adding a non-electrolyte? So you know if you have to take care of that Van Hoff factor. But for the most part, these problems are straightforward. So we'll do some of these in class, and we'll see you next time.